This week we're heading towards calculating the derivative. The derivative relates to our instantaneous rate of change. You can also think of it as the slope of the tangent line, which we've explored those kind of abstractly. We've been estimating them visually. This week we're actually going to get to calculating it. And how we end up calculating it is using our difference quotient. Before completely going into applying that and working with a bunch of different functions, let's talk about it a little bit in context of this application. So with this, we have a skydiver who broke a world record. This is from 2012, so that world record might be broken again already. But it was a high altitude dive from 127,850 feet. Free fall for 4 minutes and 20 seconds, so a total of 260 seconds before he deployed his parachute at 8,420 feet. So we're interested in his velocity while in free fall. How fast was he going? So in terms of the vertical distance covered, we started at 127,850 feet and then opened up the parachute at 8,420 feet. So that would be a total of 119,430 feet. So average velocity, we have that distance covered over a period of 260 seconds. And then I'm actually going to call that distance negative there, because this would be a negative velocity, which would be a negative 459.35 feet per second. So that's the average velocity over the entire 260 seconds. But what we want to do is zoom in and talk about instantaneous velocity. What was his speed at different moments in time during the free fall? Because what we're going to see is there's going to be moments in time that he was going a lot faster than just 459.35 feet per second. So we have our function here that we're looking at for the free fall, and we're just going to focus on the first 50 seconds of the free fall because that's where we can really see a difference in velocity occurring. So how we can tell that the velocity is changing is, like, if I look over the first 5 seconds, it looks like the height has barely changed. There's been a little change, but not much. So 5 seconds elapsed and not much difference in height. Whereas in the last 5 seconds, 5 seconds have passed, but a lot of height has been covered in comparison. So with that, his velocity is getting faster over these first 50 seconds. So is he traveling at a constant velocity? No, because the rate of change is changing. If it was a constant velocity, this would be a graph of a straight line. We would need a constant slope for it to be a constant velocity. But because this has curvature to it, that means we're going to have different rates of change. If you just imagine secant lines through each of our kind of 5-second intervals here, we can see that slope of the secant line is changing to the point that if we want to understand where is he traveling the fastest, it looks like on this graph, it's the last 5 seconds there between 45 and 50 seconds, because if we graph that secant line, that would have the steepest slope to it. So I'd say probably going fastest 45 to 50 seconds. And how can you tell? It would have the secant line with the steepest slope. And that would be talking about an average over 5 seconds. If we wanted to talk about the instant that he was going fastest, we could think about drawing tangent lines on this, which it looks like at the end here it's looking pretty linear. So the tangent line there might be pretty similar to what we're seeing there. This is also just a very low sloping graph, so it might look similar, but like if we took the tangent line up here, it's not quite as steep. So same thing of probably the steepest tangent line would be at the end of this graph as well. Okay, so what we're going to do is focus in on what's happening at the 30-second mark. And what we're going to do is first talk about average rate of change 20 to 30 and 30 to 40. So looking at the slope of the secant line between those 2 points. And then what we're going to do is zoom in a little bit closer with being only 1 second away. So at 29 to 30 and 30 to 31, and looking at the secant lines between those, or the slope of the secant lines. So I already filled in the numbers here. I grabbed these from the function up above, so looking between 20 and 30 seconds, if we plug that into the function, then we would have these outputs. So 30 would give us the 113,450, 20 would give us the 121,450. And again, the function was given to us up here as 127,850 minus 16t squared. So with that, we can calculate our average rate of change. So our AROC formula of take the difference in the outputs divided by the difference in the inputs. So we see this velocity of negative 800 feet per second. If we look between 30 and 40, again, plugging those values into the function to get our outputs divided by our inputs, we can see it's getting faster, or he's getting faster, with a velocity of negative 1,120 feet per second. So then what if we zoom in? Well, if we zoom in 29 to 30, so 29 to 30 would give us an average rate of change of negative 944 feet per second. And between 30 and 31, we see an average rate of change of negative 976 feet per second. So in part, or yeah, question 3 here, where it's the 20 to 30, 30 to 40, it's a pretty big window of what we're seeing if we're trying to get an idea of what's happening at exactly 30, but zooming in a bit, we get a clearer idea of, okay, maybe we're going to be around 950 feet per second. Still don't know for certain, but we have an instinct of, if I want to graph the tangent line right here at 30 and find the slope there, I have an estimate by looking at those values that were 1 second away. So we went 1 second below, 1 second above. So now what I want to do is think about, what if I wanted to get even closer? So this is where we think of, instead of saying exactly where our other point is, we know we're interested in what's happening at 30 and the output at 30. And what I want to do is think about a second point that's somewhere that is 30 plus some distance. And it could be to the right, it could be to the left, doesn't matter. And then I want to evaluate what's happening at the function output. Because then if I can think about the rate of change between these 2 points where I have this distance, it's this horizontal distance of h right here, I want to see what happens as I shrink that distance down to a 0. It can't equal 0 because if we're landing right on that spot, everything's going to become undefined. But we want to get infinitely close to 0, and that's where our limits come in. So what we're going to do is take this average rate of change between our outputs over our inputs, which should be 30 plus h minus 30, which all just turns into having h in the denominator. So our difference quotient comes through, and then what we want to do is evaluate this. We want to evaluate the limit of this as h gets closer to 0. So since we have our function, we're actually going to calculate this through. So if I go to this next page here, we're going to break this apart into little steps. So let's say I just want to find, what does f of 30 plus h look like? And we're working with the idea that our function f of t is that 127,850 minus 16t squared. So if I plug in 30 plus h into that function, that would be 127,850 minus 16, and then my input is now 30 plus h, and that's being squared. And then what we need to do is simplify this. So this is a scenario of plugging into a quadratic function, which we'll look at more examples with this in a future video. But when we're plugging in, if it helps, you can always take that step to rewrite it, that we're taking 30 plus h times 30 plus h. Because a common mistake would be to make that 900 plus h squared, which is not correct. But if we write in this format, then maybe it's clear that we actually need to FOIL this. So we're going to FOIL out that multiplication of two binomials. So I have my 127,850 minus, I'm keeping that 16 outside there, and then I'll have 30 times 30. I'll have a 30h plus 30h, so 60h, and then plus h squared. So there I multiplied my binomials with foiling. Now I'm going to distribute the negative 16 in. So I'll have the 127,850 keeps hanging out front there, and then 16 times 900, I'll have negative 144,000. And then we'll have a minus 960h minus 16h squared. And then my very last step is going to be to combine like terms. And I'm also going to rearrange this into standard form, which means I put my variable in descending order. This isn't required by any means, but it can help with organizing information. So negative 16h squared minus 960h. And then we'll have a plus 113,450 from combining those two values, which I had too many zeros there. I felt like something was wrong. So 127,850 minus 14,400 would get us our constant there. Okay, so all of that to simplify f of 30 plus h. Now let's go to what would it look like to have our difference in output. So f of 30 plus h minus f of 30. So what we just found there, that negative 16h squared expression, can completely replace f of 30 plus h. So I'm just going to copy down what we found up above there. And then what we're going to do is subtract f of 30, which just comes from plugging into our function. So I'm going to subtract f of 30, which is 113,450. And then let's go ahead and simplify by combining our like terms, which would be those two constants, which actually cancel out with each other. So all we're going to have is a negative 16h squared minus 960h. Okay, so that takes care of our numerator with the difference in outputs. Now let's bring in our denominator, which would usually have our difference in inputs, but it all simplifies to h. So in the numerator, we just saw that that simplifies to a negative 16h squared minus 960h. And we are dividing that by h. And what we need to do here is cancel out the h. If you're comfortable with canceling, just make sure it cancels over addition or subtraction. But the best way to really approach it, which I know it's an extra step, is to think of factoring first. So we have a common factor of h up in that numerator, and we could leave everything else alone. And then because we're dividing by an h, those are going to cancel out, and then we can see what we have for our leftovers, which is just negative 16h minus 960. So what we have here is, if we have some value for h that's a certain distance away, this would be calculating our average velocity between those 2 points. So what we want to do is to get our velocity at exactly 30. That's the idea of evaluating this as h approaches 0. So it was all about that difference in outputs over the difference in inputs, which just simplified to h, and we want to evaluate the limit as h approaches 0, which what we just found is that that would be the same as evaluating the limit as h approaches 0 of negative 16h minus 960. Which now we have something that we can just use direct substitution with, so we can just plug in 0, which is going to give us negative 960. And that right there, feet per second, is our instantaneous velocity at t equals 30. So we have the time that we're interested in, and then what we do is evaluate at that time that difference quotient as a limit as h approaches 0, and that can give us our instantaneous velocity. So comparing that to the speed of sound, at this moment in time, we are not passing the speed of sound. Could be happening elsewhere on this graph. As we saw, things got faster to the right of t equals 30, but at exactly 30 seconds, 960 is too small to be breaking that speed of sound. So all of this to say, we're headed towards evaluating these limits of the difference quotient at points in our function.